As you're doing your content page and taking your notes, we have come across this. And they're talking about gamma rays, X rays, ultraviolet rays, infrared light. These things, these waves or rays, are very important for this entire unit. So I'm going to give you a little background on it. First thing I want to say is that this topic can get very complicated. I'm going to try to break it down to the basics. You might come up with some questions. I can answer any question you have, but you have to understand that to fully understand all of these concepts, you need a lot more science and a lot more physics. But there's only one way to start, and that's to get the basics. So here's what the basics are. What we want to realize is that when we're looking at this, we see X-rays, UV, infrared, radio, and these squiggly lines. These are waves. What you're actually seeing here is the electromagnetic spectrum. So a spectrum is like the full range of something. So when we look at the electromagnetic spectrum, what we're actually seeing is the full range of wavelengths. Apologize for my terrible typing. Full range of wavelengths of energy that exists in the universe. So something that's very important to understand is that energy is the same thing as light, is the same thing as heat, and we also call it radiation. All right. So when you experience energy, you can experience it as light. Obviously, you know, like really bright lights give off heat. That's also considered radiation. Radiation energy, the form of waves. Uh, this electromagnetic spectrum, when we're looking at it, as you can see here, really short waves, really long ones, that's not actually what it looks like in the universe. In reality, that's showing you all the possibilities. But if you have a certain type of energy, for example, let's say high energy, you would see a very tight wave flying through space at you. Now, low energy, you would see very big waves. You would very rarely see something that has a long wavelength and short wavelength. This doesn't really happen in the universe. Something that gives off energy either gives off a long or a short wave or something in between. So now the thing is, since scientists realize that energy and light, heat, and radiation exist as waves, they realize that, well, there's different types. So how do we separate them from each other? The biggest way, and the one we're going to focus on the most, is by wavelength. I would definitely write this down in your notes. The wavelength is the distance between two waves. And usually we say two wave peaks has to be the same spot on two waves, right? So as we see over here, this wavelength is much longer than this wavelength, right? Now, something that is important to understand also is that wavelength tells us something about the energy. Smaller wavelength, really can't type that length, means higher energy, and vice versa. Longer wavelength means lower energy. Right? So if you see two waves coming at you through space, you see a very short wavelength wave and a very long wavelength wave. You definitely want to get out of the way of this short one because it has more energy. Now there's also another term. There's something called frequency. Frequency, if you just think about the word, that means the number of waves that pass a point over a given time. But something crazy about energy and about light and heat is that it all goes the same speed. We call it c. It's the speed of light. Obviously, right? Light goes the speed of light. So that means energy goes the speed of light. Heat, everything. So if you were to stand here and put a device straight up and try to record the frequency of these two waves, you would notice that since they're going the same speed, the one with a shorter wavelength will have a higher frequency, right? So we can add here smaller wavelengths. Shorter wavelengths means higher energy and higher frequency. And then longer wavelengths means less frequency. So let's check out a couple of these different types of waves. There's a scale. It goes from about 10 to the 8th to 10 to the negative 18th. So if you were looking at waves on this side of the scale, they would be very big. Then they get smaller. We're talking about wavelength here, and even smaller. Oop, something wacky happened there. Big, tighter, tighter. Smallest wavelengths of all, right? 10 to the 8th, that's 1 with 8 zeros, 3, 4, 5, 6, 7, 8. That's how many meters long these waves are. That's like radio waves are that big. They're huge. And also, radio waves, they have a long, super long wavelength. They have low energy. We use those for a lot of different technologies, and they don't hurt us, like the radio in your car. Now over here, 10 to the negative 18th, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 0.00001 meters long. That's very short wavelength. Gamma rays are like that. And if you know anything about gamma rays, they're very harmful, high energy. Or they can hurt you. Something to note, though, is that somewhere down here, right around this range, is what we call visible light. Now, visible light, let me rewrite that, is the only kind of light, the kind of energy that our human eyes can see. It's pretty crazy. If you looked out in space, all of these different wavelengths of energy exist, but we can only see right here. Everything, raw, red, orange, yellow, green, blue, violet, indigo, all the colors, everything you can see right now falls into this wavelength right here. So scientists realized, well, if we could see these other wavelengths or detect them, we could learn more about the universe. So that's what they do. Crazy thing, though, they learned is that some of these types of wavelengths are blocked. So here, let's look at it first and we'll talk about it. If you were out in space and you looked at it, this is what it would look like in visible light. You can learn a lot about this. But scientists know, because our sun is so close, they can read our sun actually releases gamma rays. So if we look out in space in the form of gamma rays, look at that. You can see all of these highly gamma ray emitting objects out here, and you can learn more about the universe. Now, I know what some of you might be saying. If we can't see gamma rays, how come we can see this blue and orange? What this actually is, is the things that detect gamma rays in space send information back. They tell us how much gamma rays are being emitted, how frequently, what areas have more gamma rays than others. So then we use machines to turn that into colors that we can see so that we can visualize it. This isn't actually what it would look like if you're in space, but if you could see gamma rays, it would look something like this. Check it out. If we look at X-rays, we see the universe differently too. Some things release X-rays, some don't. And as we go through these different wavelengths using instruments, we can see different things. And it helps us learn more about the universe. So understanding waves and what they are helps us make tools that allow us to see them. For example, these big satellites here, these are to detect radio waves. We can't see them, but we can detect them and turn them into something that we can see and learn more about the universe. Crazy thing, though, is that since the Earth has a magnetic field, some of the rays, some wavelengths are blocked, like gamma rays are blocked. If they weren't, that'd be really bad for us. So what scientists do is they make things that can detect gamma rays and they send them up outside of our atmosphere so that we can detect them and learn from them. If you have any questions, just come ask.